Somewhere in the deepest image the James Webb Space Telescope has ever taken, there's a smudge of light so faint that most software would have quietly deleted it as noise. It is dimmer than almost anything else in the frame, redder than it has any right to be, and sitting in a part of the sky that looks, at first glance, completely empty. But that smudge is not empty space. It is a galaxy. And the moment scientists confirmed exactly how far away it actually is, an uncomfortable question started spreading through the astronomy community, one that nobody has fully answered yet. How did something like this exist so early that it should not have had time to exist at all? Stick with me to the end of this video, because by the time we are done, you are going to understand why some of the most experienced astrophysicists working today are looking at this discovery and admitting quietly but seriously that our picture of the early universe might be missing something big. Let's start with the basics, because the scale of what we are actually talking about is almost impossible to hold in your head on the first try. Light moves at roughly 300,000 kilometers every second. Nothing in the universe travels faster, but the universe itself is so unbelievably vast that even at that speed, a single beam of light can spend more time crossing space than our entire planet has existed. Earth is roughly 4.5 billion years old. The universe is roughly 13.8 billion years old, which means there is light out there right now, arriving at our telescopes tonight, that left its source before our planet, our sun, and our solar system had even formed. That is the category of light we are dealing with here. And this particular galaxy sits about as close to the absolute beginning of everything as anything we have ever managed to detect. To understand why that matters so much, you first need to understand what the universe actually looked like in its earliest days. Because for a long stretch of cosmic history, there was nothing to see at all. No galaxies, no stars, no light, just an enormous dim cloud of hydrogen and helium gas drifting outward into darkness in every direction. Astronomers call this stretch of time the cosmic dark ages, and the name is not just dramatic flourish, it is a literal description. The gas was so dense and so widespread that you had somehow been floating in the middle of it. With your eyes wide open, you would have seen nothing but black in every direction for hundreds of millions of years. Eventually, gravity did what gravity always does over long enough timescales. Denser pockets of that gas began pulling in more material, collapsing further under their own weight, heating up, and eventually igniting into the very first generation of stars the universe had ever produced. These were not gentle stars like the one warming our own solar system. They were massive, violent, and burned through their fuel extremely quickly. Their radiation was intense enough to rip electrons away from the surrounding hydrogen gas, carving out clear, transparent bubbles inside what had been an impenetrable fog. As more and more of this first stars ignited, those bubbles kept growing and merging together until the fog lifted almost completely. Scientists call this transition ionization, and the point where it began is what astronomers now refer to as cosmic dawn. Every telescope capable of looking deep into the universe is, in some sense, trying to catch a glimpse of that exact sunrise, the very first flicker of light in an otherwise dark universe. For years, the record for the earliest confirmed galaxy sat with an object whose light had traveled toward us for an almost unimaginable length of time, dating back to when the universe was only a few hundred million years old. Every time a new candidate pushed that record even slightly further back, it made headlines, because each step closer to the beginning represents genuinely new territory, a part of cosmic history we had never directly observed before. This new discovery did exactly that, and it did it by a wide enough margin that it forced a second, much closer look. The way scientists actually confirm distances like this is worth understanding, because it explains why nobody simply takes these claims on faith. When light travels through an expanding universe, the expansion itself stretches the wavelength of that light, shifting it further toward the red end of the spectrum the longer and further it has traveled. Astronomers call this redshift, and it works almost like a built-in clock. The high are the redshift, the earlier the light left its source. Researchers first spot a candidate because it behaves strangely, showing up clearly at longer infrared wavelengths, while essentially disappearing at shorter ones. Exactly the kind of signature you would expect if its light had been so heavily redshifted that the blue end of its spectrum was stretched completely out of the visible range. That pattern alone is enough to flag an object as promising, but it is not enough to confirm anything. To actually prove the distance, scientists have to point the telescope directly at the object and run its light through an instrument that splits it into individual wavelengths, essentially the same way a glass prism splits sunlight into a rainbow. When that spectrum comes back and lines up with what a specific redshift predicts, the distance stops being a guess and becomes a measurement. None of this would have been possible without the telescope itself, and it is worth pausing for a moment to appreciate exactly what that telescope had to do to make a discovery like this even possible. The James Webb Space Telescope carries a primary mirror more than 6 meters across, built out of 18 individual gold-coated hexagonals, segments that had to unfold with total precision after launch, a sequence of hundreds of individual mechanisms that all had to work correctly on the first try, with no chance of a repair mission if something went wrong. It sits roughly 1.5 million kilometers from Earth, far beyond the orbit of the Moon, at a gravitationally stable point where it can stay shielded from the light and heat of both the Earth and the Sun at once. That shielding matters enormously because the telescope is built to detect infrared light, the same part of the spectrum given off by warm objects, which means the telescope itself has to be kept extraordinarily cold to avoid drowning out the faint signals it is trying to catch. Every part of that engineering exists for exactly one purpose: to catch light so faint and so stretched by cosmic expansion that no previous instrument could have reliably detected it at all. Without that specific combination of size, distance, and sensitivity, a galaxy like this one would have simply remained invisible, its light arriving at Earth after billions of years of travel, only to pass straight through us undetected. Researchers finally ran this galaxy's light through that process. The numbers that came, when back were extreme, even by the standards of recent discoveries. We are talking about light that left its home galaxy when the universe had lived through only a small single-digit percentage of its entire current age. Let's try to actually picture what that means in practical terms. Imagine compressing the entire 13.8 billion year history of the universe down into a single calendar year. The Big Bang happens in the very first second of January the 1st. This galaxy is already shining by sometime in the first 2 weeks of January. Dinosaurs do not show up until the day after Christmas. Every single human being who has ever lived fits inside the last few minutes before midnight on New Year's Eve. And somehow we built a machine, launched it roughly 1.5 million kilometers from Earth, unfolded a mirror the size of a tennis court in the vacuum of space, and used it to catch a single particle of light from the opening days of January. Here is where the real problem begins, and it is not really about the distance itself. Astronomers have gotten reasonably comfortable with the idea that galaxies can form earlier than older models predicted. The real issue is what this particular galaxy looks like once you actually examine it closely. It is small, tightly compact, nowhere near the size of a fully mature galaxy like our own Milky Way, and yet it is remarkably bright, putting out far more light than something that young and that compact has any business producing, according to standard models of galaxy formation. Those models predict that galaxies at this stage of cosmic history should look messy, dim, and still in the process of slowly pulling themselves together. This one, instead, looks organized, energetic, and almost too well developed, as if it skipped several stages of normal galactic adolescence entirely, and arrived early to a party nothing else was supposed to have reached yet. So what could actually be powering something like this? Scientists have floated a handful of possibilities, and each one comes with implications that would force a real rewrite of some part of the existing textbook. One option is that star formation in the extremely early universe was simply far more efficient than anyone assumed, with gas collapsing into new stars unusually fast, and without the typical inefficiencies we observe in galaxies today. Another possibility is that the very first generation of stars ever formed were so massive and so intensely hot that a relatively small number of them could genuinely outshine what we would expect from an entire mature galaxy. And a third possibility, the one that tends to generate the most attention, is that something else entirely sits at the center of this object. Potentially an extremely early black hole actively feeding on surrounding material and radiating enormous amounts of energy in the process. Every one of these explanations would require scientists to meaningfully revise something they currently consider close to settled about how the early universe actually worked. There is also a fourth, more exotic possibility that occasionally comes up in discussions like this one, the idea that some of the earliest structure in the universe could trace back to what are called primordial black holes, hypothetical objects that would have formed directly from extreme density fluctuations in the first fraction of a second after the Big Bang, long before any star had ever ignited. If seeds like that existed, scattered throughout the early universe, they could have given gravity a serious head start, pulling surrounding gas together and accelerating structure formation well ahead of the timeline predicted by standard models. Nobody has confirmed that primordial black holes actually exist, and most astronomers still treat the idea as a minority position rather than a leading explanation. But discoveries like this one are exactly the kind of evidence that keeps that possibility from being fully ruled out either. But surprisingly, the brightness is not even the strangest part of this discovery. When researchers examined the full spectrum of light in more detail, they found something buried inside the surrounding gas that genuinely puzzled them, a specific chemical signature involving unusually high levels of certain heavier elements relative to what basic physics would predict for a galaxy this young. This detail matters more than it might sound like at first, because heavier chemical elements are never free. The universe was born containing almost nothing but hydrogen, helium, and a tiny trace of lithium. Every other element that exists, including the carbon in every living cell and the oxygen you are breathing in right now, had to be manufactured inside the cores of stars first, and then violently scattered back into space when those stars eventually died. Building up any meaningfully enriched chemical environment takes multiple full generations of stars living, dying, and recycling their material back into their surroundings. At an age measured in a few hundred million years, there should have barely been enough time for a single full generation of stars to complete that entire life cycle, let alone enough overlapping generations to produce the kind of chemical signature researchers actually detected here. There's a second layer buried inside that same finding that makes it even stranger. That particular chemical fingerprint has also been observed much closer to home, inside extremely dense, ancient clusters of stars that orbit around the outer edges of galaxies, like our own Milky Way. These clusters have long been treated as some of the oldest structures in the universe, relics from somewhere within the first few billion years of cosmic history. If a galaxy this young is already displaying that exact same distinctive chemical pattern, it suggests that whatever process actually builds structures like these may have started operating almost the moment the early cosmic fog cleared away. That does not just nudge the existing timeline slightly earlier, it compresses it in a way that is genuinely difficult to explain with current models. At this point, you might reasonably think this is simply one strange, unusual object, an outlier that occasionally shows up in any large enough data set. Except this is not an isolated case sitting off in a corner somewhere. Ever since the James Webb Space Telescope became fully operational, it has been returning some version of this exact same surprising result over and over again. Galaxy after galaxy, spotted deep in the early universe, keeps turning out too bright, too structurally developed, and too chemically advanced for the specific moment in cosmic history we are catching it in. What researchers originally expected to be a small handful of rare exceptions has quietly turned into something that increasingly looks like the standard result instead, not the exception to the rule, but a pattern running straight through the data. This matters enormously, because the current scientific framework describing how large-scale cosmic structure assembles over time did not come from guesswork. It represents decades of careful observation, detailed computer simulation, and repeated testing against real data, and it has genuinely survived an enormous number of those tests successfully. That framework is not simply wrong, but it does keep getting surprised again and again in exactly the same direction, and a scientific model that keeps getting surprised consistently in the same specific direction is almost certainly missing something real. Maybe dark matter played a more aggressive role in seeding the earliest cosmic structures than current models probably account for. Maybe the physics governing that very first generation of stars is meaningfully different from anything currently sitting in the existing scientific catalog. Maybe there is some mechanism actively operating during the first few hundred million years of cosmic history that scientists have not fully identified yet. None of that represents science failing at its job. That is actually science doing precisely what it is supposed to do, running directly into a genuine wall of contradictory evidence and refusing to simply look away from it. It is also extremely likely that this particular record will not stand for very long. Researchers working on these deep field surveys have already said publicly that the James Webb Space Telescope appears fully capable of pushing this frontier back even further, potentially reaching redshifts that were considered completely out of reach only a few years ago, edging ever closer toward the era of the very first stars the universe ever produced. Every new observing cycle gives scientists another chance to catch light from a little bit earlier, a little bit closer to the true beginning, and every time that happens, we get a slightly clearer picture of exactly how fast the earliest galaxies actually managed to come together. I want to be genuinely fair and balanced here, because there is also a simpler, more cautious way to look at all of this, and intellectual honesty requires putting it clearly on the table. Discoveries at the very edge of what our instruments can detect are, by definition, working with extremely limited data. A single galaxy, measured once, can look far stranger than it actually is simply because of how little context we have to compare it against. Early measurements sometimes get meaningfully revised once additional data comes in. Some of what looks completely surprising today may end up looking fairly unremarkable within a decade or two, once our instruments and our models both continue to improve, and once we have a larger sample of similar galaxies to compare this one against instead of treating it as a lone outlier. Extraordinary claims genuinely do deserve extraordinary scrutiny, and the scientists behind this work know that better than anyone. That is exactly why they keep pointing the telescope back at objects like this one, chasing more data instead of simply accepting the first surprising result at face value. But here is the honest, balanced takeaway to actually walk away with. Not that our existing models of the early universe have been proven wrong, and not that this discovery should be dismissed as some kind of fluke either. The honest position is that we are currently looking at a growing pile of separate, seemingly unrelated pieces of evidence, all quietly pointing in the same uncomfortable direction at the same time. Galaxies forming and organizing themselves far faster than expected. Chemical enrichment showing up far earlier than the standard timeline allows. And a telescope that keeps finding more examples of exactly this same pattern every time it looks a little further back. Somewhere in the very early universe, a tiny, unusually bright patch of light began its journey across an expanding cosmos, carrying a genuine scientific puzzle inside it the entire way. It traveled for the better part of 13 billion years, patiently waiting for someone, somewhere, to eventually build a mirror large enough and sensitive enough to finally catch it. We just did exactly that. And the very first thing this discovery tells us is that we currently understand considerably less about how the early universe actually assembled itself than most scientists confidently assumed only a few short years ago. So what do you think is actually going on out there? Drop your honest thoughts down in the comments below. And if this kind of deep space mystery genuinely fascinates you, make sure you are subscribed to this channel. Because we cover discoveries exactly like this one on a regular basis, real findings straight from real published research, explained clearly without unnecessary exaggeration. Because, once again, the more we manage to see of the early universe, the stranger it seems to get